So this is the outline of the work. I want just to underline that the main objective of this work was the analysis of the linear orthotropic behavior under compression of a lattice configuration that was the combination of the body cubic and the octet truss topology. The final result were the distribution, the stress and strain curve distribution of a set of these configuration of BCO. So the idea of this study was born by our work, preliminary work with the shape memory polymer. And in particular, you know very well that as an example, a material like PLA, the polylactic acid, has this capability to deform temporarily. So depending on the stimuli. So the PLA is sensitive to the temperature. So if the temperature is low, we have a low stimulus, external stimulus, we have a high Young modulus that as soon as the temperature increase and exceed the glass transition temperature, we'll see a transformation of the Young modulus, so a drop of the Young modulus and the transformation of the material in a soft elastometer. This idea, this concept of the transformation in our mind was associated with the concept of degradation. And so we wanted to apply, therefore, the idea of evaluate a combination of basic unit cell in terms of degradation. So we created a new topology, let's say new material, the BCO combination that was constituted by a topological combination with two unit cell plus also a combination of two different materials. And we wanted to analyze how the mechanical property of this BCO structure change depending on the stiffness ratio. So the first step was the selection of two basic unit cells. So just a brief recall. So this is an example of unit cell topology. You see that you have nodes and struts, and there is a simple equation, the Maxwell criterion, that can help you in understanding if a unit cell type can be classified as bending dominating or stretching dominating. So in our work, we selected the body cubic unit cell that is a bending dominated, and then we selected the octet that is a stretching dominating unit. So we practically design via finite element analysis our topology. I will call in the next slide, just for simplicity, BC as a cubic. And also we designed the octet, and we put together, so combine these two unit cells in a third topology, the BCO, that we analyze in depth. So you know that the mechanical property depends not only on the topology, so on the geometry, but also on the parameters. So it depends on the cubic sides of the topology, on the section of the strut, and on the relative density of the wool design. In our study, we evaluated three different strut section ratio, one circular, so B over A equal to 1, and two of ellipse shape. And at the end, the combination, the BCO, was evaluated for three different relative density. In terms of material, so I have already said to you that the combination is not only topological combination, but is also a combination of materials. So we decided to take from the literature the Young modulus of the PLAs as material 1, that in our concept, the material 1 is the material as it is originally, so not degraded. And then we selected also as input the Young modulus 3.149 megapascal as material 0, that is an example of degrading PLA. So when it becomes a soft elastometer. So just to recall a bit all the steps that we go through. So we first design in our simulation the two topology, the cubic and the octet. Then, of course, we set for this topology the parameters. So the cubic size was 1 per 1 per 1 millimeter. 3 different cross section for the strut shape in our set of configuration, with 3 different relative density for the BCO structure at the end. And in fact, the combination that we evaluate, so the set of combination that we evaluated were created by the 2 different topology combined together, plus 2 different material. And we analyze how the decay change the mechanical property, analyzing 2 different stiffness ratio, A1 over A0 equal to 1 and equal to 1000. In terms of finite element analysis, we use the Abacus software. So we tested the behavior under compression, apply a displacement of 1 millimeter. The final output were the stress and strain curves. So I want to just show you the result. On the right, you have here an overview of the parameter that we set. In particular, the strut shape in such a case is a circular shape for the strut. The design here has a relative density equal to 0.2. And the combination you see in total, we created a set of 4 combinations. Here, if you read the column, you have the topology of the cubic with 2 different materials. Material 1 is the stiffer material. Material 0 is the softer. Similarly, if you read the combination along the line, material 1 is the octet with stiffer material. Material 0 is the octet with the softer material. So here you may see on the left the combination, therefore, of our structure BCO that is composed by an octet that is stiff, okay, and a cubic that is soft. And this is the typical deformation that you may observe. If you have instead this other combination with an octet that is soft and a cubic that is stiff, you have this type of deformation. So if we go in detail to looking at all the 4 combinations, and you have here the color code that are similar to the color code of the line, you see the stress and strain curve, and you may observe that, for example, the green curve here show that is the combination A1 over A0 equal to 10 minus 3 as a stiffness ratio, show a behavior that is very similar to the curve, the line in black. The line in black is the BCO combination of 2 stiffer material, okay? While if you look at the top plot, that is just a zoom in of this part of the bottom illustration, you may observe that the red curve that has stiffness ratio equals to 1000 behaves similarly as the blue curve that is the combination of the BCO constituted by 2 soft material. So what does it mean this in terms of degradation? As an example, if you have the octet that is degrading going from the black curve to the red curve, so changing the stiffness, the stiffness. So you have first that the combination is provided by 2 materials that are in good original form, so not degrading, and then both the 2 material becomes a sort of soft elastometer. So in such a case, you have that the overall structure, the BCO, is not performing from the mechanical point of view, so in terms of strength and stiffness, well. In this result, you see instead still some issue in terms of convergence. So this is a sign that this study is on its preliminary stage still, but you may observe that in general, all the 4 combinations show clearly the linear region and the buckling region. And in such a case, as an example, if we show the degradation of the cubic, so going from material 1 stiff to material 0 that is soft, so going as an example from the red curve to the blue curve, we see that the BCO has overall performed quite well. So we, in any case, high effective stiffness. In this last result, we have instead a stress and strain distribution that is a bit different respect to the previous two slides. And the reason is that even if the strut shape is elliptical as in the previous slide, here the relative density is higher. And so we have a change of a failure mode from a instability to a yielding failure mode. Sorry. Here I have reported all the summary of the result. So you have here the color code as in this matrix. In the illustration here, this is the topology. So the octet is provided by the diagonal external line, while the cubic is underlined, let's say, by this internal cross. The black means that the material is stiffer, so material 1, while the yellow means that the material is softer. Close to the curve, you have the relative density of the BCO, while the full line show the cross-section that is circular, and the dotted line show the cross-section that are of ellipse shape. So what we can observe in the overall from this preliminary study is that if we increase the density, we have a better mechanical performance, so higher stiffness and strength. Then we may observe that in the case of a combination, so a BCO that is created by a cubic that is soft and an octet that is stiff, even if we change the relative humidity, the relative density, so we increase the relative density, the stiffness doesn't change too much. We can also observe that if we go from the curve in black to the curve in red, so we can go from this illustration to this just degrading the octet, so the octet become softer. In such a case, we see that the overall performance of the BCO structure is worse. So as a conclusion, we can say that this is a preliminary study. We have investigated the mechanical performance as a function of the stiffness ratio for this topology, these two topology, the combination of cubic and octet under compression using the finite element analysis. From the combination, we can say that is the octet the most sensitive topology that when it's degraded can have a big effect on the whole combination. And we can say that this work is still at the preliminary stage because of some issue with the convergence and because we just evaluated a single representative volume element, and we need to work more on multi-volume element in the future. So, thank you very much.